Yeah, one of the problems with speaking like on the third day of a conference, especially one like of this quality, is that I'm like get so much inspiration and talk to so many people that I have all these ideas about making my talk better, so I keep changing it. So hopefully I'll be able to get through it without stumbling. We'll see what happens. I'm also very sleepy. Yeah, my name is Rob. I work for the Gemini 8-meter observatory. So we have 2 telescopes that are very big. One is in Hawaii and one is in Chile. I write software that helps scientists use them to do science. So it's fun work. I also work on some open source projects, including some of them that we're going to talk about today. You can't hear me? All right. All right. So how many of you, if you don't mind saying, have used either Scala Z or CATS? Oh, quite a few. Oh, that's great. Were any of you in John DeGoe's talk about Cofree or Greg's talk about Matryoshka? Okay, good. So some of this stuff is going to seem familiar probably. So that'll make it a little bit easier. So today I kind of want to just talk about some odds and ends that I think are interesting, and we'll see if you find them interesting too. So our goals for the talk, the big one is to start kind of developing an intuition for Fixpoint types. This stuff is pretty well known in the Haskell community, but not so much among Scala programmers. And these are really interesting general purpose data types that I think we should know more about because they're really useful. We'll learn a little bit about doobie, which is a database library that I work on. It's a pure functional interface for writing JDBC programs. Gain some confidence pushing on code. So this is something that I mention a lot when I'm giving talks, and people don't know what I'm talking about, so I'm going to try and illustrate what I mean by pushing code around. And importantly, don't panic. Okay, so everyone who's a functional programmer can remember when they were having trouble learning recursion. It's hard. It's a mind-blowing thing, learning recursive functions, inductive data types. And what we're going to be talking about today is doing these sorts of things at the type level. And it is hard. And if you're confused and struggling a little bit, that's okay. And I promise I will try to reel you back in and make sure it's understandable. I have been told to hold this in my hand. All right. Okay, so let's get started. Let's look at a recursive data type. Okay, so here is a simple recursive data type, and the idea is these are university professors and their PhD students who also became professors. So we have a case class, we have a name, and we have the year they got their PhD, just so we'll have some data. And then the students are a list of professors. So it's a recursive data type. And if you look down at the bottom, there is an example. There's David Hilbert with 3 of his students, and Weil and McLean have a couple students down there as well. So the kind of invented, sort of the example that I want to work through is taking a structure like this and trying to map it to a relational database in a natural way and then read it back. And we'll use that example to develop some ideas. So if you were going to store this kind of thing in a relational database, this is probably what you would do. You would have I have to take off my glasses because I can see my screen or you. The natural SQL representation is going to be a table. You're going to have some generated identifier. You will have the name and the year as columns, and then you'll have this parent column that's a pointer that goes the other way. The children reference their parents. So the relationship that's natural in the database is sort of inverted from the natural relationship that you have in your Scala data type. So we'll have to figure out how to deal with that distinction. But the first thing I want to do is talk about what we're going to do with that database ID. We got to figure out how to represent that on the Scala side. So here's one way we might do it. Just add an int field. Can anybody see any issues with doing it that way? Anyone? Yeah. Repetition? Well, I guess the problem that I see with it is when you just construct one of these things and it hasn't been in the database, you don't have an ID, right? So you need some out-of-band value there, so a -1 or something, but that we use types for that kind of thing in Scala. Otherwise, you're going to be constantly checking to see if it's a real ID or not. So, so we might do this and use an option of int. Is that any better? It's a little better, right? But I think this representation is still pretty irritating because really you have three cases, right? Either you've just constructed it and you know that it's new and it has no ID, or you just pulled it from the database and you know that it does have an ID, and you still have to check the case where it might be missing, which is irritating. And then you might be doing some sort of computation over this structure, displaying it for the user or something, where you don't care about the IDs, and you have this cruft from the database that has sort of infected your data type. So I think this isn't a very good encoding either. So one way we might do it is try and externalize the ID and have something like this. So we have a type alias where ID prof is a pair of the ID and the prof. Okay? Can anyone see a problem with this representation? Anyone? Okay, so, well, what about the students? The students don't have IDs, so we have to do this, right? So the int is back into our case class again, which defeats the purpose. So here's where we're going to kind of make a leap, and I'll show you this is the one trick, basically the one trick in this presentation. So we don't know what type to put there, so I'm just going to introduce a type parameter. And you may start to feel uncomfortable from this point on, but I'll try to pull you back. Okay. All right. So now our data structure is no longer recursive. Okay. A prof, and I've renamed it profF just to distinguish it from our original prof data type. And the students, the children, are a list of anything at all. Okay. So now what we can try to do is say, okay, well, our prof type is a profF whose children are also profFs. Okay, and the ID prof is a pair of an int and a profF whose children are pairs of int and profF. And what is the problem with that? ProfF needs a type argument, right? So if you actually want to write this out correctly, you end up with that. Okay, so that doesn't work, right? Because the types are infinite. So we can try something else. We can do that. So we can say, all right, prof is a profF of prof, right? So we're referring back to the type alias. So we're going to try and tie the knot that way. And the same thing with ID prof. It's a pair of int and a profF of ID prof, which is itself a pair of an int and a profF of ID prof. And does that work? That does not work because type aliases cannot be self-referential in Scala. But we can do it with a class. Classes can be self-referential. So what about that? So we've just turned it into a case class in both cases. And that compiles, and that works. Okay? So now we have a single data type, profF, and two different representations of it. We have sort of the flat tree with no database artifact, and then we have the one with the IDs associated with it. And that works, and that compiles. And we could claim victory and just be done. But this is functional programming, it's Scala, and we like to generalize things. So let's push on this a little bit and see what happens. So we'll notice that in prof and ID prof, there's nothing in the implementation that is specific to profF. It could just be any unary type constructor. So we can factor that out, right? And on the right-hand side, the recursive case, the profs need to take an f as a type argument. Okay, so we've just factored out profF. And then also in ID prof, there's nothing specific to ID being an int, so we can just make that any type A. And then again, the A has to appear on the self-referential portion over on the right. Okay, so this is interesting. We have something that's absolutely generic. There's nothing specific to our domain here anymore. Both of these things are potentially very useful because they have solved a concrete problem for us. So that always makes me very skeptical. Anything I invent that is sufficiently polymorphic and plausibly useful probably is already a thing, right? And it's probably a thing in CATS or ScalaZ or both, or some FP library. So I'm not clever enough to invent something that is as useful as what we just did. And it turns out that both of these types are, in fact, very well known. Okay? The first one is called fix. Okay? And that gives us a fix point for any functor f. It lets us write that infinite type in a finite way. Okay? And the second one is called Cofree. Okay? And it does the same thing, but at each node in this structure, you have an arbitrary annotation. Okay? And if you saw John's talk yesterday or the day before, whenever it was, you have some idea of what a cool type that is, and we'll explore it a little bit. While I'm here, I'll mention one other data type, and you can guess what it is. So Cofree is an A and an F, and this other type is an A or an F. Does anyone know what this type is called? Very good. That's free. Okay? So Cofree gives you a structure with labels at each node. Okay? And free gives you an equivalent structure with labels with values down at the leaves. And that's kind of the difference. Okay? Free is commonly called the free monad because if f is a functor, then free is a monad. With Cofree, if f is a functor, then Cofree is a comonad. Okay? So it's worth pointing out that the implementations of free and Cofree in cats and Scala Z are much more complicated than this, right, if you've ever looked at them. And there are two reasons for that. The first one is you want to be able to define these things so that they're arbitrarily large or maybe even infinite. So they have to be lazy. You can't evaluate them strictly like this does. And you also need a way to traverse these very large things without blowing the stack. So you have to have machinery that allows you to do that. So those are the sources of complexity in cats and Scala Z. But, and it's unfortunate because they're really very simple fundamentally, but it's hard to know that just looking at the implementations in the FP libraries. I think it's a really fun exercise to take this definition of free and build it out, define map, define flat map. To define flat map, you will discover that f has to be a functor. You can build it out so that you can write little DSLs and interpreters and interpret them. It'll be strict and it'll be finite, but it will work and it'll give you a good intuition about how all this stuff fits together if you've just been using this free pattern mechanically, like I did for a long time. Okay, so I want to point out a few more things before we move on. If we have a Cofree, we can always get an F out of it. So we can always take a layer off, but we can't do that with free because there might not be an F in there. You might get an A out. And then if we have an F, we can always construct a free, but we can't do that with Cofree because you also need an A. So on that basis, on the basis of that distinction, we can define recursive and co-recursive types and abstract over them. And that's something that Matroshka does for you. And just for free, you get this huge just explosion of operations that you can perform on types that are like this. So there's some really nice general stuff that's going on. So if you saw Greg's talk on Matroshka, you'll have some inkling about that sort of stuff. In this talk, I'm going to build everything from scratch. So some of the things I'm going to show you, you would get for free with Matroshka, and I'll try and point that out. The last thing I want to point out before we leave, before we continue, is that both Cofree and free are Fixpoint types. So if we look, we see they each reference themselves in the same way that prof did, and we can apply the same trick. We can just add a type parameter, and now we have Cofree f, where we just introduce a b for the recursive part, and the same thing with free f. And now we can define Cofree and free as fixed points of those new functors that we've defined. So that's just to show you that there's something really general going on here, which is kind of interesting. Okay, so enough of that. So now we know the general types, and we can define prof and ID prof trivially. Right, so prof is just fix of prof f, ID prof is Cofree of prof f annotated with integers. Okay, let's see if I can put this thing back. So I think I may have lost some people at this point, so I'm going to try and back up and try and make this less scary if possible. So here is our original data type, right? And here's the construction that maps to the tree down to the bottom. So take a look at that and become confident that you understand how that fits together. Okay, so now let's look at the fix version. Boom, okay? It's the same structure. All we're doing is wrapping it in an extra constructor. There's nothing mysterious about it. It's just a construction, okay? And then the Cofree case, same thing. It's just like fix, just like the original one. It's the same structure, except at each value, we also associate an annotation, okay? So this is just data, right? We can construct it, we can pattern match on it. There's nothing mysterious about it. The types are kind of intimidating and the names are kind of intimidating, but it's just data, just like anything else. So please don't be scared of it. Okay, so before we get back to the database problem, I want to do some programming with these types that's just in a pure context that doesn't have any database, any I/O effects to worry about, because that'll make it a little more complicated. So let's write some parsers. Okay, so here we have we have some data. It's a tree structure, and we use indentation to indicate the nesting. So you might recognize some of those names. So what we want to do is parse this into our Fixpoint types. So here's one way we could do it. This is using a parsing library called Addo, but it would look the same using Howey's quick parse library or really any other monadic parsing library. So what are we going to do? We're going to, the idea here is this will parse a fix of prof f at some given indentation. So we're going to skip the initial indentation. We're going to read the name, and then skip the comma and the space, read the year, skip a new line, and then the magic part is we will call ourselves recursively and read many of these things at an increased indentation. So now we have what we need. We have the name, the year, and the children, and we can yield the fix of prof f. Okay? And that works. The toString is not very useful, so I wrote a method that will draw it out, and I'm not going to show it to you, but it's in the example code. Okay, and it works. So, so we've got the prof f structure, the fix of the prof f structure back. And let's see what we can do it with Cofree. So here's our fix parser, just with some extra lines in it. And here's one with Cofree that's a little bit different. So look at the change, right? It's the same structure. We just have a couple extra things happening. So what we're going to do is read the parse position in, and then do what we just did, and then read the parse position when we're done. And then what we're going to yield is a Cofree that's annotated with the starting and ending position. Okay? And that works. And what we get back is this. We get back the tree where each prof f is annotated with its position in the input string, which I think is really cool. So our original reason for doing this is so we could annotate these things with database IDs, but we can use that slot for anything. So here we're using it for parse positions. You can see how this structure would be really useful for doing something like a programming language, where your functor is some AST for your programming language, and then you can parse it in, and then you can annotate it with source positions and inferred types, or do strictness analysis, whatever. All sorts of stuff, and none of those annotations muck around with your AST representation. So you have a separation of concerns, and you have a really simple data type, and something else is giving the annotations for you. So that's really nice. Okay, so before we get back to the database program, I want to explain something that you might have been wondering about, which is where did the f come from? So it turns out prof f is a functor, and this means we can map over it. Now, if you follow this design pattern, it's always going to be a functor, and in fact, it's called a pattern functor. So prof f is the pattern functor for prof and for ID prof. They differ in the recursive structure that we're applying externally, but it's the same underlying functor. So in any case, the A only appears in the students, so we can just kind of delegate to map to the map operation on the students member. So if we look down at the bottom, we have a prof f of string, and it doesn't mean anything to us, but it's okay, it's a valid type. And if we map to s.length, we get a prof f of int back. So that's fairly straightforward. It turns out we can do better than that. Prof f is a traversable functor. So that's even better. That means we can sequence it. So if we have a prof f of g of a, we can turn that into a g of prof f of a. if G is an applicative functor. So don't worry about the implementation. Look down at the bottom and just look at the types. So we have a proff of option int, and when we sequence it, we get an option of proff of int. Okay, so it flips those outer type constructors. That's a really useful thing to do. It happens all the time in monadic programming, so if you don't know about traversable and applicative functors, it's something you should learn about because you really can't do monadic programming without these things. Okay, so we defined this traverse operation up here, but what we called down here was sequence, so I want to show you what the relationship is. Okay, so the definition of traverse tells you that map f followed by sequence is the same thing as traverse. Okay, and that's just by definition. And from that we can use equational reasoning to find another identity. So fa is the same thing as fa map identity, which is the functor law. fa.sequence, so we'll just sequence both sides of that, so that has to be the same. But we know map identity followed by sequence is the same thing as traverse identity. So we now know that fa.sequence is the same thing as fa traverse identity. So when you're programming with these things, it's good to know the relationship at the top and at the bottom, because depending on what's more performant or more convenient, you can just swap one for the other. All right, so let's talk about database programming. Let's talk about doobie. So doobie is a pure functional database layer for Scala, or in particular JDBC layer. It's very specific to JDBC. There are no side effects. Doobie programs are values. It's built for Scala Z and for cats as of the most recent milestones. This is a new thing. It's a type level project that I'm very proud of, and I do have stickers for doobie and other type level projects if anyone's interested. I had 10 slides in my presentation to try and explain this, explain how doobie works, and I think it's not enough if you don't understand programming with free monads, and it's too much if you do understand it. So what I'm going to do is kind of give you an executive summary of how doobie works, and then if you find yourself confused at some point later in the talk, just stop me and I'll explain. I think the documentation for doobie is good, and there's some other presentations on YouTube that you can watch about it. Okay, so the ingredients of doobie. So we have algebras for all the operations for all the JDBC types, so result sets, connections, things like that. And that defines the primitive operations that we can use. We have the free monads of those, and that gives us 16 little languages with 1,000 operations that we can perform on them. And that gives us composition. That gives us a way to take these atomic operations and build programs with them. We have lifting operations that let you combine programs that are written in these different languages. So you can have a connection program and a prepared statement program, and you can embed one in the other. And then there are some built-in interpreters that will take you from these doobie types into something like Scala Z task or Monix task or something like that, IO-like data types. So this stuff is all very low level. This lets you write JDBC level programs in a functional style, which is very low level. It's not very convenient. So there's some higher level stuff as well. So there's some constructors that let you get away from the integer constants and irritating things like that JDBC gives you. So we have proper enumerations and that sort of thing. There are resource-safe constructors that let you say, okay, if I've constructed a prepared statement, I don't actually get to see the prepared statement. I can give you a prepared statement program that will handle it for me and execute it. And that prevents you from being able to leak these things. You can't leak a connection or a result set or anything because the type never appears anywhere when you use this API. You can't get a handle to the thing that you might want to leak. There is type mapping that allows you to read things out of a column and map them to a data type. And then a new thing that I'm working on is compile time checking of SQL literals, and we'll see a little bit of that in a minute. Okay, here we go. So let's insert a tree. So recall our profF type. So the first thing we're going to do is make a program that inserts a profF, just ignoring the children and returning the generated ID. So this insert node method takes an optional parent ID and then the profF that we want to insert. And what this constructs is a program that will do something with a database connection and give us an int back. So what we have here is a SQL literal. It uses some Postgres specific stuff to do an insert and then return the ID, which is nice. We support all of that stuff. The interpolated arguments are not an injection risk. This thing gets turned into a program that prepares the statement and does the properly typed setting, set string, set int at different indices, so that's safe. And then the unique int says, okay, we expect exactly one row back and one column that will contain an int, which is what we want. Okay, yes?
What's the parents? Why is there no students?
Right now we're just doing the flat insert, and we're going to come back and do the students later. Okay, so I'm going to get rid of this profF definition to make some more room. Okay, so here is the method that inserts the fix of profF and returns an equivalent tree. Okay, so this takes an optional parent, and it takes this fix of profF, which is, as you recall, is just the flat structure, just this nested structure with no annotations. And what we're going to do is go to the database, insert that thing, and return an equivalent tree that has the ID, the annotated nodes with the IDs on them. So we take, again, an optional parent and the fix. So we don't know how to do anything other than insert the nodes, so we'll do that. That gives us a connection IO of int. And we need to return a connection IO of something else, so we're going to flat map. So we're doing this in a for comprehension. So we get the profF. We recursively map the children over this insert tree operation that gives us a profF of connection IO of cofree profF of int, which is almost the type we want, but not quite. We need the type constructors to be swapped, so we call sequence. So that gives us the head and the tail that we need to construct the cofree. Okay, so intuitively, really all we're doing is we're just trying to do we're mapping this operation over the children. You just need to use traverse in a monadic context. So recall that map followed by sequence is just traverse, so we can simplify that. Okay, so we can generalize this a little bit more. With Matryoshka, you could do this with a coalgebra without a recursive call, but we're just going to leave it here for now. Yes?
Can you say again what unfix is?
Unfix, yeah, so if we go back to the definition of fix, where is that? Sorry, it's way back here. Okay, so unfix just gets the member out. That's all it does. Okay, where are we? Insert a tree. Okay, good. So that's our insert tree program, and it works. So we are going to parse that data back like we did before, and I'm going to call insert tree on it with no parent. And then transact XA, that's something I'm not going to show you. That just associates this operation with a database pool, and what we get back is an IO program that we can actually execute. So I'm flat mapping that into another program that I'm not going to show you that draws the cofree and the IO monad for us. And when we run that, it goes out to the database and inserts everything and then returns it with the annotations. Okay, and the reason the numbers are so high is because I've been compiling these slides over and over and over and over, and there are a bunch of copies of this thing in the database. Okay, so that's the hard part. So now let's talk about reading it back. So here's read node. And what it does is it takes an ID and it returns a program that will read a profF whose children are ints. So what does that mean? All right, so that's a profF whose children are database IDs. So a way to think about this is we have one node in the graph, and if we want to step off the graph, we got to go back to the database and fetch more. Okay, now I'm going to acknowledge this is a very inefficient way to do this. We're doing 2 selects for each element. The way you'd really want to do it is load everything in memory and unfold it in memory, but then I would just be talking about SQL, and it's not very interesting. So in the example code, I show how to do that. So what are we doing? So we are going to get kind of the data. We're going to get the name and the year for the row we've asked for. And then we're going to get the IDs of all the children that are associated with it. So we're going to get a unique pair of string and int for D, and then a list of int for S's. And that's all we need to construct the profF. Okay? So that gives us sort of one local node in this tree. What if we wanted two levels? What if we want to be able to take a step before we go back to the database? We can define that. So we can read one and we get something whose children are IDs, and then we can do it again on the children by traversing, and now we get a profF of int. So that means we can sort of take one step and get another profF, and then take another step, and we've got an int and have to go back to the database. And we can do 3 if we want to. We can actually generalize over that with by indexing this operation on a type level natural number. We can say, okay, I want to read 10 and then terminate with an int. That's in the sample code if you want to see it. So this is an interesting thing you might want to do if you have a graph and you want to show it to the user, but you only want them to see part of it. You don't want to load the whole thing from the database. You just want to load sort of a little local region. This would allow you to do that. And the types keep track of where you are, which is kind of nice. Now, we could load just sort of an arbitrary subgraph where each child is either an ID or it's a node. It's one thing or the other. Does anyone know what type we might use to do that? That's free, right? So now free pops out. This is kind of contrived, but this just reads a tree. It'll stop whenever it hits an even numbered database ID. So it's loading an arbitrary region of this graph out of the database, which can be useful because you can decide kind of on the fly whether you want to keep going or stop with an ID and force the user to hit the database again if they want to go farther. So I'm not gonna take this apart. You can look at it in the sample code if you want to. But so really what we wanted to be doing is just read the whole thing back with the annotations. That's the problem we're trying to solve. So let's get back to that. Okay, so here we go. This is easier than what we did before. So we have the ID, so we're going to read node. We're going to say read node, which gives us a connection IO that gives us the profF of int. So PI is profF of int. We need a connection IO, so we've got a flat map. So now we're going to map over the children with read tree. That's our recursive call. And then we'll sequence it to flip the type constructors. And then we have everything we need to construct the cofree. So we'll map and construct it. So we know map followed by sequence is traverse. So we can simplify that. So that's a pretty compact little method. So I want to take a minute and look at this method more closely and see if we can generalize it a little bit. This works, but there's something more general here. So let's factor out the call to read node because that is specific to our problem domain. So we'll just pass in some f that gives us an int to a connection IO of profF of int. F gives us a connection IO back, but the only thing we're ever doing with it is calling flat map and then map. So it'll work with any monad, right? So we can factor that out. And now we get an m of profF int, but the only thing we're ever doing with profF of int is calling traverse on it. So we can factor out profF, it's just any traversable functor, right? And we've got this int that we're taking, but the only thing we ever do is pass it to f. So we can factor that out too. Okay? So this is the same thing that happened before. We have something that's totally generic and it's useful, right? And we're not clever enough to invent it ourselves. So this is just the effectful unfold for cofree. Okay? And what it does is it says, if you give me some seed value and a way to unfold it, I'll just continue unfolding it forever until I get to the end. Okay? And you would get this for free if you were using Matryoshka. This is another thing that you just get from the library if it's there. It's not in Scala Z or CATS. I think it probably should be. So, but even so, I think going through an exercise like this is helpful because even if you're only calling this method one time in your program, it's worth generalizing like this because the more polymorphic your method is, the more polymorphic your code is, the fewer ways there are to write it. Okay, which means the fewer ways you have to write it incorrectly. Okay, so you can save yourself from making a lot of dumb mistakes by going through this exercise when you can. Okay, so in any case, now that we have this, our read tree method is trivial. We just delegate to read node and we're done. And does it work? It works. So I'm a little embarrassed by this because as I said, I've been inserting so many copies of this tree, I actually have to find an ID, and there are a lot of them. So I find one ID that matches Hilbert. So that's what that first program does. It's not very interesting. And then I flat map it into read tree, and then I print it out, and it does work. So it fetched out Hilbert's subtree and printed it out. So that kind of ties the knot and everything works. Okay, so I want to point out that I think it's really cool that we're doing this just totally generic monadic unfold, and we're not thinking about database operations in our code, right? We haven't talked about threading a connection through or iterating over result sets or doing any of this stuff. We're programming with these database operations just like any other kind of data, which is what you want, everything works the way you would expect. All right, so let's review a little bit. What have we seen? So we learned about some Fixpoint types. Okay, so Fix and Cofree popped out pretty fast. Free came along a little bit later. And we got to them just by pushing on our model, and not really that hard. These are natural things that are useful, and we should learn how to use them. And we use them to represent the same data type in a bunch of different ways, right? Cofree was really awesome. So we have a simple recursive type. We have sort of an isolated node with no child information. We have a tree annotated with parse positions. We have nodes with database references. We have partial deserialized graphs. And then, of course, we have the full graph with the database IDs, which is the last thing we built. And we did all of that with the same definition of profF. We never changed that after whatever slide, wherever it appeared, slide 3 or something. And we pushed our code around. You see what I mean. You can generalize, 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 and sometimes you wind up with something that's interesting. And hopefully you all survived. I know this stuff is hard. The sample code has a lot more examples, and there are a lot of comments in it. So if you look at that and review the slides, and just contact me if you have questions. I'm very easy to find. And hopefully you'll find a way to use this in your programs. And that's all I got. Thank you very much. Okay, let me point out, if you look on GitHub, my Cofree repo has all this stuff in it. If you're interested in recursion schemes, look at Slam Data, Matroshka, and Sellout recursion scheme talk. It has a lot of great stuff in it. If you're interested in doobie, there's a lot of good stuff on the website. And I wanted to point out that 47 Degrees put in they made a Scala exercises module for doobie if you want to play around with it online. It's really cool. I think I have time for half a question. Anyone?
What?
What? I don't have time to answer that. Okay, yeah, long.
Is there a further generalization for profF? You kind of modeled that. I was wondering if there's anything more you can say about it.
I don't know. I haven't thought about that. Possibly. I mean, it's an example. I mean, yeah, you could. I mean, you could say, okay, well, it's just a rows tree, and pull out the it's Cofree of list, and the annotation is the name and the year, and that structure is just a list that gets unfolded over and over. Yeah, so you could generalize it if you wanted to. I mean, at that point, it might not be very convenient, but you can. They're isomorphic. You can turn one into the other. Yeah, good question. Okay, we're out of time. Thank you.